What if your smartphone's frame was actually its battery? What if your car's body panels could power the entire vehicle? Swedish scientists just made this science fiction reality. Welcome back to Curiosity AI, where we explore the scientific breakthroughs that are reshaping our world. Today, I'm bringing you a story that could fundamentally change how we design every electronic device and vehicle on the planet. Professor Leif Asp and his team at Chalmers University in Sweden have achieved something that seemed impossible. They've created batteries that are stronger than aluminum while storing electrical energy. These aren't just batteries with better cases. These are materials that serve as both the structure of your device and its power source simultaneously. Think about your smartphone for a moment. Right now, it has a battery pack taking up space inside, plus a metal or plastic frame providing structural support. That's two separate systems doing two separate jobs. The Swedish breakthrough eliminates this redundancy entirely. The frame becomes the battery becomes the frame. The implications are staggering. We're talking about smartphones as thin as credit cards with current battery life, electric vehicles with 70% longer range without adding weight, and aerospace applications that could revolutionize how we build everything that flies. This isn't just an incremental improvement, it's a complete paradigm shift in materials science. To understand why this breakthrough is so revolutionary, let me explain how these structural battery composites actually work. Traditional thinking about batteries and structures treats them as completely separate problems. You design a battery to store energy, then you build a structure to hold everything together. But what if the same material could do both jobs at once? The Swedish team uses carbon fiber as their secret weapon. Carbon fiber is already famous for being incredibly strong and lightweight. It's used in Formula One race cars and aerospace applications. But here's the breakthrough. Carbon fiber can also serve as an electrode in a battery. The design works like this. Carbon fiber serves as the negative electrode of the battery. A second type of carbon fiber coated with lithium iron phosphate serves as the positive electrode. Between them, there's an incredibly thin separator, only 30 micrometers thick, that allows ions to flow back and forth. The magic happens when you cure this entire system into a rigid composite. You end up with a material that's mechanically stronger than aluminum, while simultaneously storing electrical energy. The structure is the battery, and the battery is the structure. The performance numbers are mind-blowing. Their latest prototypes achieve over 60 watt-hours per kilogram of energy storage while maintaining an elastic modulus exceeding 100 gigapascals. To put that in perspective, that's approaching the energy density of conventional batteries while being stiffer than many metals. The breakthrough moment came through years of systematic improvement that reads like a materials science success story. In 2021, the Chalmers team's initial prototypes achieved 24 watt-hours per kilogram with decent mechanical properties. Most experts thought that was interesting but not revolutionary. By 2024, they'd pushed performance to 30 watt-hours per kilogram while dramatically increasing stiffness to 76 gigapascals. But 2025 brought the game changer. Prototypes exceeding 60 watt-hours per kilogram with elastic modulus values surpassing 100 gigapascals. This represents double the multifunctional performance compared to their previous generation. But here's what makes it truly revolutionary. These latest prototypes demonstrate exceptional cycle stability, maintaining approximately 100% efficiency over 1,000 charge-discharge cycles. Think about what this means. You have a material that's stronger than aluminum, stores substantial electrical energy, and maintains its performance through thousands of cycles. It's like discovering a new category of matter that doesn't follow the usual trade-offs. The manufacturing process itself is an engineering marvel. They use vacuum-assisted infusion of a biphasic solid-liquid electrolyte system that cures into a rigid composite structure. This technique, adapted from aerospace composite manufacturing, ensures both electrical functionality and mechanical strength are optimized simultaneously. This Swedish breakthrough is positioning Scandinavia for potential leadership in what could become a multi-billion-dollar market transformation. While other nations focus on traditional battery improvements, Sweden has opened an entirely new technological pathway. The market projections are staggering. The structural battery technology market is valued at $1.6 billion in 2025, with projected compound annual growth rates of 16% through 2033. But these numbers may underestimate the true potential if the technology achieves widespread adoption. Sweden's early leadership, anchored by Chalmers University and spin-off company Synonys AB, creates significant strategic advantages. This isn't just about technology, it's about economic transformation. The Nordic region could become a global center for advanced materials manufacturing, much like how Silicon Valley became the center for semiconductors. The competitive dynamics are fascinating. Traditional battery manufacturers have shown limited interest, viewing structural batteries as niche applications. This creates opportunities for new entrants and could reshape the entire energy storage industry hierarchy. China's dominance in conventional battery manufacturing might be less relevant in a structural battery world, where materials science expertise and composite manufacturing capabilities matter more than scale production of lithium cells. This could rebalance global competitiveness in energy storage technologies. Automotive manufacturers are expressing intense interest. Every electric vehicle manufacturer struggles with battery weight and packaging constraints. Structural batteries could solve both problems simultaneously, potentially triggering a new round of EV innovation centered around Swedish technology. Let me paint a picture of how structural batteries will transform the devices and vehicles we use every day. Starting with consumer electronics, Professor Asp envisions smartphones as thin as credit cards while maintaining current battery life. Think about that for a moment. Your phone could be literally paper thin because the frame itself is the battery. No more thick devices, no more battery bulges, no more trade-offs between thinness and battery life. Laptops could see 50% weight reductions while gaining longer battery life. The structural battery would replace traditional internal frames while providing power, creating ultralight portable computers that professionals have been dreaming about for decades. But the really exciting applications are in transportation. Electric vehicles could integrate structural batteries into chassis panels, reducing overall vehicle weight by 20 to 30%. This weight reduction would translate directly to approximately 70% increased driving range without adding any additional battery capacity. Think about the physics here. Lighter vehicles require less energy to accelerate and maintain speed, so you get a compounding benefit. The structural battery reduces weight while providing the same energy storage, and the reduced weight makes that stored energy go much further. The aerospace industry shows perhaps the strongest interest. Aircraft manufacturers constantly seek weight reduction opportunities because every kilogram saved translates directly to fuel efficiency or payload capacity. Structural batteries integrated into non-critical components could provide auxiliary power while reducing aircraft weight. Military applications could be revolutionary. Unmanned aerial vehicles could achieve extended flight times through structural battery integration in wing structures. The drone's wings would literally be flying batteries, powering extended missions that are impossible with conventional designs. The development trajectory for structural batteries follows a clear but ambitious path that could reshape multiple industries within the next decade. Short-term developments through 2027 focus on refining energy density and mechanical properties while developing manufacturing processes suitable for pilot production. The team targets energy densities exceeding 60 watt-hours per kilogram while maintaining elastic modulus values above 100 gigapascals. Consumer electronics will likely see the first commercial implementations because these markets accept higher costs for performance advantages and have shorter development cycles than automotive applications. Smartphone and laptop prototypes incorporating structural batteries may appear within the next 2 years. The medium-term outlook through 2030 brings automotive applications transitioning from research to development programs. Pilot programs with automotive manufacturers will test structural battery integration in non-critical components before advancing to primary structural elements. Manufacturing scalability becomes crucial during this period. Current production methods, adapted from aerospace composite manufacturing, need evolution for automotive and electronics volumes. The industry must solve automation and quality control challenges while reducing costs through economies of scale. Long-term vision through 2035 anticipates mass market adoption of structural batteries in electric vehicles as performance, cost, and manufacturing capabilities reach automotive industry requirements. Vehicle designs incorporating structural batteries may fundamentally change automotive architecture. Energy density and mechanical property improvements will continue through materials innovation and manufacturing refinement. Advanced carbon fiber treatments, novel electrolyte systems, and optimized composite structures should push performance boundaries even further. The Swedish breakthrough in structural battery composites represents more than just another materials science achievement. It's a fundamental reconceptualization of how we integrate energy storage into the devices and vehicles that define modern life. Professor Leif Asp's team has demonstrated that the traditional separation between structure and energy storage is artificial. By creating materials that excel at both functions simultaneously, they've opened possibilities that seemed like science fiction just a few years ago. The progression from 24 watt-hours per kilogram in 2021 to over 60 watt-hours per kilogram in 2025, combined with mechanical properties exceeding aluminum, validates the enormous potential of this approach. We're witnessing the birth of a new category of functional materials. Sweden's leadership in this field positions the Nordic region at the forefront of what could be the next major materials revolution. As smartphones become credit card thin and electric vehicles gain 70% more range without adding weight, structural batteries may prove as transformative as the introduction of lithium-ion technology itself. The challenges ahead are significant, encompassing manufacturing scalability, safety certification, and cost reduction. But the fundamental scientific breakthroughs have been achieved, and the path to commercialization is increasingly clear. For industries seeking weight reduction, energy efficiency, and design flexibility, structural battery composites offer unprecedented opportunities. The integration of structure and energy storage eliminates fundamental inefficiencies that have limited device and vehicle design for decades. Thanks for joining me on Curiosity AI today. If this exploration of Swedish materials science innovation fascinated you, subscribe for more deep dives into the breakthrough technologies that are quietly revolutionizing our world. Next week, we'll explore another scientific achievement that's challenging everything we thought we knew about what's possible. Until then, keep questioning, keep exploring, and remember that the most transformative technologies often come from reconsidering the most basic assumptions about how things work.